Hello, everyone. My name is Chen Yu. I'm from the University of Washington. Today, I'll introduce our work, NEMO, Guiding and Contextualizing Weak Supervision for Interactive Data Programming. Before we start, I'd like to thank my amazing collaborators, Jayyu Zhang and Alex Ratner. In the past few years, we have seen that data collection has become one major bottleneck in machine learning. As modern machine learning models get bigger, they are more data hungry. But manual labeling large-scale data sets can be very expensive, like building ImageNet or MS-CoCo for vision tasks, or building NLP datasets like Squad for question answering. To tackle the data collection challenge, one promising alternative route to traditional manual labeling is weak supervision. The central theme of weak supervision is to leverage cheaper but noisier forms of supervision to create training data sets quickly. Among different weak supervision approaches, data programming is a very popular approach that allows users to programmatically build data sets through user-defined labeling functions. For example, if we are to build a sentiment classification data set, instead of hand annotate the data points one by one, the users create what we call labeling functions to programmatically label the datasets. The labeling functions, for example, can be a Python code snippet that checks whether the word great is in the input sentence and return positive sentiment correspondingly. Of course, the labels assigned by individual labeling function can be noisy, but in aggregation, they can be close to the ground truth labels. More specifically, the data programming workflow consists of three main stages. In the first labeling function development stage, users encode labeling heuristic into labeling functions. As the labeling functions can conflict with each other, in the second stage, a label model will be used to aggregate the output labels. Finally, we can then use the labeled datasets to train our favorite models, like in standard supervised learning setting. Indeed, data programming has led to many successful use cases and practical applications, but the final outcome is very dependent on the provided labeling functions, as they are the central supervision inputs to the entire pipeline. The current practice to create these labeling functions is through an iterative process. Starting with an unlabeled dataset, we randomly sample different data points to show the users for them to come up with ideas for labeling functions. Because of these practice, we observe that the developed labeling functions are much affected by what data point the user is seeing in the development stage. More specifically, we observe that labeling functions are more likely to cover data points that are close to the data points shown to the user, and these labeling functions are more accurate around these development data. Well, we see that the labeling functions are much affected by what data points the user is seeing in the development stage. The entire labeling function development process is typically ignored and treated as a black box by existing works. This has led to two major problems. First, consider that we have two labeling functions covering the two big clusters. Ideally, we would want the new labeling function to cover a smaller cluster. But instead, the current practice of random sampling is likely to give us the data points in the big clusters again, resulting in a redundant and efficient labeling function creation. And second, we drop the information on what labeling functions are created from which data points, which can be very useful in resolving the conflicts between two labeling functions. To tackle the challenge, we propose interactive data programming. We formalize the labeling function development cycle as an interactive procedure and study two core problems within the framework. First, we study how to strategically select data to guide the user in developing informative labeling functions. Second, we study how we can leverage the information on the connection between development data and the resultant labeling functions to help better denoise and aggregate the weak labels. Based on the framework, we propose NEMO, a system for interactive data programming. The system starts by taking as input an unlabeled dataset. Then in each iteration, the NeMo backend development data selector strategically selects data points to show to the user. The user then uses NeMo's front end to develop corresponding labeling functions. By tracking the connection between the selected data points to the resulting labeling functions, NeMo contextualizes the labeling functions to help better denoise and learn from the labeling functions. Let's dive into each of these components. First, at the NeMo front end, the user can create labeling functions from the selected data points. For example, in a sentiment classification task, when prompted by an example, perfect for my workouts, it makes my yoga classes much more fun. We first ask the user to determine the label of the example. In this case, it's a positive sentiment. Then the user selects the keyword primitive that is indicative to the positive label. In this case, assume that the user selects perfect. Then we can create a labeling function, return positive if the sentence contains the keyword perfect. At the NeMo backend, recall that one goal of NeMo is to efficiently guide users in creating informative labeling functions. Towards the goal, we propose a selection strategy named Select by Expected Utility, or SEU. The core idea of the selection algorithm is to choose the example that has the highest expectation of leading to the most useful labeling functions. Specifically, for each example, we model the probability of it leading to different labeling functions by p lambda given x. Then, for each labeling functions, we measure its utility by its informativeness and its accuracy using a function psi. We can then summarize and calculate the utility of each example by calculating the expected utility of the labeling function it could potentially lead to. We then select the most useful example in each iteration. After the labeling functions are created, NeMo then utilizes their data lineage to contextualize and denoise them. The core idea is simple. Consider that a user is shown the example, the movie is really funny, and created a labeling function. Funny indicates positive. While this labeling function holds, for example, within movie review, it can fail on examples on restaurants review, like the food tastes funny. To tackle this problem, we propose to restrict that labeling functions to be active only within a local neighborhood of the original example shown. We show later in the experiment that this simple technique in leveraging the lineage between the development data to labeling functions can much improve the model's denoising performance. To validate the effectiveness of NeMo, we compare it to a suite of interactive learning approaches on 5 different datasets across sentiment classification and spam classification tasks. Specifically, we compare to existing methods that can fit under interactive data programming framework with different selection and contextualized learning strategies. In addition, we also compare to other interactive schemes, including traditional active learning and interactive weak supervision. In the experiment, we see that NeMo consistently achieves the best performances on all datasets we tested on compared to all other methods, where we observe an average performance improvements of 20% and up to 47% on the SMS dataset. We also conducted ablation studies to validate the effectiveness of the individual components within NeMo. Specifically, we validate that the proposed SEU data selection method achieves the best performance compared to all other existing selection strategies, including random sampling, abstain-based, and disagreement-based selection methods. Furthermore, we also verified that the contextualized learning method always leads to performance improvements when compared to the baseline without using contextualized learning. To summarize, while weak supervision offers a promising route to reduce costly human supervision, its current labeling function development practice is underexplored and suboptimal. In this work, we introduced NeMo to improve the efficiency of weak supervision by formalizing the labeling function development process through the proposed interactive data programming framework. We then tackled the data selection and labeling function denoising challenges through the proposed SU selection method and contextualized learning method, respectively. Thank you for listening. Please feel free to reach out for any questions.